Hi class, Bob Greavy. I'm going to walk you through a couple of problems from your simulation chapter and explain what in the world's going on here. So what I'm going to do is start by reading number 2 from your textbook. Number 2 says the management of Madeira Manufacturing Company is considering the introduction of a new product. The fixed cost to begin the production of the product is $30,000. We've listed that on the spreadsheet right there. Okay. The variable cost for the product is expected to be between 16 and 24, and you'll see those numbers listed here, and you'll see all of this again in a couple of formula. The product will sell for $50 per unit. Of course, we've got that listed right there, the selling price. Demand for the product is expected to range from 300 to 2,100 units, and you'll see that in the formulas in this column right here under demand. With 1,200 units most likely. And let me walk you through how this spreadsheet works and what this spreadsheet is doing now. The first thing to understand is something called the random number generator. And if you type in Excel the following, if you just type equals rand and open and close parentheses, that will generate a number between 0 and 1. Randomly generated. So every number between 0 and 1 has an equal likelihood of appearing there. So this happened to be 0.2231425. Now, so let's look at a couple of these values down here. So first of all, each row in the spreadsheet, you see we got row 1, 2, 3, 4, 5, 6, 7, and so on. Each of these represent a particular simulation. So we're actually doing simulations for every single row, and looks like we're going to run 500 different simulations. Each row of the spreadsheet is a simulation. Let's look at this first one here. The rand between formula is just like the rand formula, only where rand generates a random number between 0 and 1, you guessed it, rand between generates a random number between numbers you specify. So in this situation, it's going to generate a number between 16 and 24, each with an equal likelihood. And you'll notice in your book, the problem told us that the variable cost to produce the product is expected to be between 16 and 24. So what this is doing is it's generating a simple distribution of variable cost. So if we were to average this column, it'd be right around 20 because every number between 16 and 24 has an equal likelihood of occurring. So you'd probably see about half roughly above 20, about half below, because 20 is right in the middle of 16 and 24. But that's what that's doing. That's generating a random event. And in this case, that random event is the cost per unit to produce this product. Now, if we look at demand, we're going to simulate an instance of demand here. Now, this formula is a little bit ugly, but what this is doing is it's simulating the results that follow a normal distribution. If you'll recall, you have a normal distribution that looks like this, and maybe at one end of the extreme you have 300, at the other end of the extreme you have 1,200. And what this is doing is it's taking, you'll recall this area under the curve totals 1% or totals 100%. And what it's doing is it's using the random number generated right here. It's using that random number that is generated in the first argument of the formula. It says equals norm I and V, the inverse of the normal distribution, open parentheses, and you see that random. So that first argument is going to be a number between 0 and 1. And what it's doing is if this is 1, it'd be 1,200. If it was 0, it'd be 300. And what it's doing is it's giving the value that would appear right here if this area to the left of that line equaled that random number. Okay? So what that winds up doing is generating a distribution of values that follow the normal distribution with 300 at the low end and 1,200 at the high end. So it's a fancy way to generate or simulate, in this example, values that follow the normal distribution that range from 300 to 1200. So, for example, if that random number that is generated in this function happened to be a 0.5, that's going to be right here because half of this area corresponds to that 0.5, and this right here would be halfway between 300 and 1200, so it'd be 750, I guess. So that's what's going on in that formula. It's simulating a particular demand that follows the normal distribution with 300 at the low end and 1200 at the high end. So what we've just done in columns B and C is we've simulated a variable cost per unit that could happen. We've simulated a demand that could happen, and we've done so in where both of these simulations correspond to the distributions described by the problem in the chapter. And then the column D represents the corresponding profit. So this is a very simple formula. If you just study it for a minute, you'll see that profit, the resulting profit, if variable cost per unit was $23 and demand was only $5.75, we'd actually take a loss. And let's look at that profit formula there. You've got C13 times C3. Let's just take that part. C13 is this simulated demand right here times C3, which is the price per unit. So this first part, C13 and C3. C13 times C3 represents our revenues. Of course, to get profit, you subtract from that the cost. So we've got 50 times 575, that's our revenues. We're going to subtract from that C4, our fixed costs. And then that last part of this equation is where we're subtracting our variable costs. B13, which is demand, times the variable cost. So fit 23 in this simulation. So if we do that, if we have revenues of $50 times 575 units, and we have costs of $30,000 and another variable cost of $23 times 575 units, then we wind up losing money. We wind up losing 14,458. So what's happening in each row, let's look at this particular row here, is the system is randomly generating a variable cost per unit, in this case 18. It's randomly generating an instance of demand, and then this is just calculating the profit that would happen if these first two things happen. And that's what's happening at every single row. So what we're doing here, by copying and pasting that row downward 500 times, we're simulating 500 potential scenarios. We're simulating what could happen, and we're doing it 500 times, and we're saying, okay, if we simulated this across 500 instances, what does that look like? And what we've done over here on the far right is, let's look at these formulas. I've just taken an average profit, and all I've done is I've looked at the average value of the profit column, and it's around 5,696 in one particular simulation. Okay, and you can, every time you do this, just go to the end of a formula here and hit enter, and it'll re-simulate. It'll rerun all those variable cost per units. It'll rerun all those random instances of demand, and it will spit out the new profits that correspond to that. So over here I've just run some quick statistics on column D, and the average profit is around $6,000. The standard deviation of that profit is huge. It's $9,000. The worst case scenario, the minimum is $32,000 and the maximum is $39,000. So you can quickly get a feel for this situation through simulation. So why do you simulate, not use queuing theory? Well, queuing theory is pretty limited in its scope. You can't do just a whole lot of things with queuing theory. And you can do about anything. You can build an example, you can build an environment using simulation, and let the computer generate the random events and let it do so perhaps hundreds of times, and then you can infer from the results of those simulations what could possibly happen. And what we've just done here is we've said, if this happened 500 different times, what's the typical outcome? Well, on average, you'd have a profit of, a little bit above $6,000, but look at those worst case scenarios and look at the potential standard deviation is a little frightening. It's going to vary all over the map. And that's the result of having variable costs all over the map and demand all over the map. So Here's one nice example of what you can do in a simple spreadsheet to perform simulation.